Hello, my name is Dennis Michael. I work for the Environmental Protection Agency, Office of Air Quality Planning and Standards. This video will illustrate a calibration of two types of meteorological equipment, the wind speed and direction sensors. It is normal practice for calibrations to be performed of both wind speed and direction at the same time. Generally, there are three types of wind sensors in use within the state and local pollution agency networks. These are cup and vane, aerovane, and sonic anemometer systems. This video will illustrate the calibration of one of these systems, the cup and vane. First, let's talk about why we need these sensors at monitoring stations. Wind speed and wind direction sensors tell us from which direction the wind is blowing and at what speed. These parameters are very important because if we want to know the direction pollution is coming from or where the air pollution is going, the wind sensors give us that information. Before we get going, let's define what we mean by a calibration. EPA defines a calibration as a comparison to a measurement standard, instrument or item with a standard or instrument of higher accuracy to detect and quantify inaccuracies and to report or eliminate those inaccuracies by adjustments. So, you can see that there are two parts of this process, primarily the measuring to conformance and secondly the adjustment to that conformance. What this translates to is testing and adjusting the instrument to see if it meets our standards. For wind speed and wind direction sensors, this means imitating either wind speed or, in the case of the direction from which the wind is blowing. The wind speed calibration is performed by spinning the anemometer sensor at a particular rate of speed, or revolutions per minute, also known as RPMs. The wind direction is calibrated by referencing a particular direction as a reference point. Calibrations of meteorological systems always take at least two people to perform. The reason is simple. While one person is performing the test on the instrument, another person must record the responses. This is a typical meteorological tower. There are several types of towers commercially available. The different types might be collapsible, tilt-down, or crank-down towers. This tower is a crank-down tower. These sensors are the Met1 Corporation Model 021C wind direction sensor and the 010C wind speed sensor. They are attached at opposite ends of the instrument support boom. Before the tower is lowered, a wind direction reference point must be determined. There are several methods available, these being the magnetic compass, geographic positioning system or GPS, or the solar noon method. These three methods are described in detail in the EPA's Quality Assurance Handbook Volume 4, which is a companion to this video. The procedures can be obtained in Section 2 of the handbook. Today we will use the GPS method. Within the last 10 years, GPS has become inexpensive, smaller, lighter, and easier to use. The unit that we will utilize is a Garmin eTrex model GPS. The GPS has many nice features such as direction, position, and altitude. We will use the direction mode to give us a reference. Turn on the GPS and it will begin acquiring signals from overhead satellite positions. Once it has acquired 3 satellite signals, it will display your latitude and longitude. Now switch to the direction mode. At this point in time, we need to decide what our reference point will be. I recommend using the instrument boom, upon which the instruments are mounted. Walk away from the shelter to a point where you can clearly see the instrument boom. Align yourself so that you cannot distinguish one sensor from the other. This means you're aligned with the boom. Begin walking toward the tower. The GPS will now determine which direction you are walking. Record this value. To double check this alignment, go to the opposite end of the tower. Perform the same procedure as before. This value that the GPS displays should be plus or minus 180 degrees of the first value that you recorded. If it is 180 degrees from the first recorded value, you have referenced the instrument boom correctly. At this time, you may now lower the tower. The first sensor is a wind speed anemometer. It works on a simple principle of a spinning chopper wheel and an electronic eye or sensor. The wheel inside has a predetermined number of holes that interrupts the light shining on the sensor. As the wheel spins faster, the light is interrupted more often. The sensor sends a signal as a square wave that is translated to the wind speed. So if we spin the sensor at a known speed, it should translate to a value in the translator and be recorded by our data acquisition system, also known as our DAS. This second sensor is a wind direction vane. It works on a simple principle of a sweeping potentiometer. The internal potentiometer is wired in a way that its position will determine the voltage that is sent to the translator. Each voltage corresponds to a different wind direction. Many wind direction sensors have a combination potentiometer that has a crossover function that allows it to record from 0 to 540 degrees instead of 0 to 360 degrees. This allows the sensor to read the directions near zero accurately. It is now time to remove the wind speed anemometer cups. This is done by loosening the Allen nut with an Allen wrench that holds the cups to the anemometer shaft. The Allen nut and wrench will be supplied by the anemometer manufacturer. At this time, take the anemometer shaft between your thumb and index finger and turn it back and forth. Test to see if there is any drag or friction that you can feel. If so, the bearings may need to be replaced. We will quantify the drag of the bearings using a torque test, which will determine the starting threshold. We will perform this test later. It is now time to begin the calibration. Calibration data should be recorded on a calibration sheet and in the station log book. The first task is to record the location, operator, date, GPS coordinates. The second task is to record the instrument make, model, serial numbers, and full-scale range. You will note that the form has two sets of tables. The first column in the top table should read calibration points, RPM. The second column should read calibration values in meters per second. At this time, we need to determine which RPMs will translate into the wind speeds. Reference your manufacturer's manual for the slope and intercept equation that translates the RPMs to wind speed. Using a calculator, enter in several RPMs into the slope-intercept equation to determine the source values at these RPMs. Generally, we would want to 0 and 3 upscale points. I recommend points at 10%, 50%, and 90% of the full-scale range of the wind speed sensor. Enter these values into the table under the headings of the calibration values. The next step is to begin the zero test of the sensor. This is a simple test. With the cups removed from the sensor, have the technician record the output of the sensor on the DAS. The 0 point will not be 0. It will be the starting threshold of the anemometer. This value will be in the manufacturer's manual. The device that we shall use to reference the upper range of the wind speed sensor is the R.M. Young model number 18802 battery-operated motor and controller unit. This unit can generate RPMs from 0 to 15,000 RPM. Notice the controller unit has a toggle switch for on-off, direction, clockwise or counterclockwise, and speed. The motor is attached to it via a cable. Once the unit is turned on, the controller controls the speed that is generated. Note the rubber grommet at this time will be used to attach the shaft of the motor to the shaft of the anemometer. The control unit allows the user to switch speeds, thus changing the response of the anemometer. The site technician is now attaching the motor shaft via the grommet or rubber tubing to the anemometer shaft. Caution should be used here. It is important that the appropriate tubing or grommet be used so that neither anemometer nor motor shaft slips. This will cause inaccurate readings. Once the rubber tubing is attached and is secure, the technician should start the motor and dial in the first value. This should be approximately 10% of the full-scale range. Once the controller shows that the speed has stabilized, the second technician should record the response of the DAS. Once the first value has been recorded, the outside technician must increase the speed of the motor to the second calibration point. This should be approximately 50% of the full-scale range. Once the controller shows that the speed has stabilized, the inside technician should record the response of the DAS. It is now time for the third and final upscale point. The outside technician will now increase the speed of the motor to 90% of the full-scale range. Once all of the points are generated and recorded, compare the recorded results against the slope-intercept generated values. If these are within specifications for your program, then the sensor or DAS does not need to be adjusted. If adjustments are made, it is recommended that you rerun the calibration points with the calibration device to reaffirm that this is true. This concludes the motorized calibration of the sensor. The torque test should now be performed. All wind speed and direction sensors that have bearings have what we refer to as a starting threshold. This is the amount of force, that is wind, that is needed to overcome the resting inertia to get the sensor moving. As bearings age, this resting inertia will increase. It is critical that the torque test be performed every time that the motorized calibration is performed. We shall be using an R.M. Young Corporation model number 18310 torque disc for both the wind direction and wind speed sensors. The torque test is performed by removing the sensor from the tower and bringing it into the shelter. On a flat surface, place the sensor on its side so that it is laying flat on the bench. Attach the torque wheel to the shaft of the sensor. A grommet or small piece of tubing can be used to make a snug fit. Now that the torque wheel is attached, place one of the screws into the middle hole on one side of the wheel. With a 1 gram screw in the third hole, gravity generates 3 gram-centimeters of force of torque. The technician holds the wheel so that the screw is parallel to the table. When the technician lets the wheel go, if the wheel moves, then the torque is less than 3 gram-centimeters. Now move the screw to the hole that is the number 2 position. Repeat the test. If the wheel moves in the number 2 position, then move the screw to the number 1 position. If the wheel moves in this position, then record the torque as 1 gram-centimeter. The EPA QA Handbook on Meteorological Measurements, section 2.5.1.1, has the equation for converting torque to meters per second. Reference your manufacturer's manual for the optimal starting threshold for your sensor. If the starting threshold is above the manufacturer's recommended value, then the bearing must be replaced. Retest the torque after you have replaced the bearing. This now concludes the wind speed anemometer calibration. Perform the maintenance on your sensor that is recommended by the manufacturer. It is recommended that once you connect the sensor back on the instrument boom and hook up the cables, that you rerun the 0 and 1 upscale point to make sure that all connections to the sensor have been connected properly. Our next task is the calibration of the wind direction system. If you remember from earlier, we used the GPS unit to reference the alignment of the instrument boom. We will now utilize this information to perform the wind direction calibration. Before we start the wind direction calibration, let's record all of the pertinent information on the calibration form. In the second portion of the form, let's record the make, model, serial number of the wind direction sensor and the equipment used to reference the instrument boom. At this time, you will need to calculate the alignment of the boom to true north. If you use a GPS, then it calculates the direction in reference to true north. If you use the compass, the magnetic declination must be taken into account. If you use the solar noon method, then you need to reference the solar noon calculator or tables. These techniques are discussed in detail in the EPA QA Handbook on Meteorological Measurements in section 2.5.2.2. In the first column, labeled calibration point degrees, record the alignment of the instrument boom that we determined using the GPS unit. In the second row, record the value, which is 90 degrees, plus the value determined for the instrument boom. In the third row, add an additional 90 degrees until the table is filled in. These values will be our reference values for the calibration. With the wind direction vane in place, have the outside technician hold the vane so that it is in line with the instrument boom. Start the test so that the weight or the head of the vane is pointing towards the instrument boom. Have the technician hold the vane as steady as possible. Once the vane is steady, have the inside technician record the response of the DAS. Once the inside technician reads the value from the DAS, have the technician move the sensor 90 degrees in a clockwise direction so that the vane is now perpendicular to the instrument boom. Use a square. This will help. The next point that will be performed is 180 degrees from the original point. Have the outside technician move the vane in a clockwise direction. With the wind direction vane in place, have the outside technician hold the vane so that the tail is in line with the instrument boom. Have the technician hold the vane as steady as possible. Once the vane is steady, have the inside technician record the response of the DAS. Once the inside technician reads the value from the DAS, have the technician move the sensor 90 degrees from the last point so that it is 180 degrees from the original perpendicular point. Remember to move it in a clockwise direction. Use of a square will help. At this time, it is important to perform the crossover test. Some wind direction systems are designed in a way so that the operation will be seamless when the vane crosses over the 0 or 360-degree line. If the sensor has this function, it is necessary to slowly spin the sensor in a clockwise position. When the vane gets to the 360-degree area, move slowly and hold the vane either perpendicular or parallel to the vane. The DAS system should read the value between 360 and 540 degrees. If it does, then record this in the last row of the calibration form. Check to see if this value is within the tolerance of the system. This concludes the alignment portion of the wind direction calibration. The torque test should now be performed. As we discussed earlier, all direction sensors have bearings that we refer to as a starting threshold. This is the amount of force, that is wind, that is needed to overcome the resting inertia to get the sensor moving. As bearings age, the resting inertia will increase. It is critical that the torque test be performed every time the calibration is performed. Note that the starting threshold of a wind direction sensor will be different from the wind speed sensor threshold. The torque test is performed by removing the sensor from the tower and bringing it into the shelter. On a flat surface, place the sensor upright on the bench. Attach the torque wheel to the shaft of the sensor. A grommet or small piece of tubing can be used to make a snug fit. Now that the torque wheel is attached, place one of the screws in the middle hole on one side of the wheel. With the 1 gram screw in the third hole, gravity generates 3 gram-centimeters of force, or torque. The technician holds the wheel so that the screw is parallel to the table. When the technician lets the wheel go, if the wheel moves, then the torque is less than 3 gram-centimeters. Now move the screw to the hole that is the number 2 position. Repeat the test. If the wheel moves in the number 2 position, then move the screw to the number 1 position. If the wheel moves in this position, then record the torque as 1 gram-centimeter. The EPA QA Handbook on Meteorological Measurements, Section 2.5.1.1, has the equation converting the torque to meters per second. Reference your manufacturer's manual for the optimal starting threshold for your sensor. If the starting threshold is above the recommended value, then the bearings must be replaced. Retest the torque after you have replaced the bearings. This now concludes the wind direction calibration. Perform the maintenance on the sensor that is recommended by the manufacturer. It is recommended that once you connect the sensor back to the instrument boom and hook up the cables, you rerun at least 2 alignment points to make sure all the connections to the sensor have been connected properly and that the sensor is aligned correctly to the instrument boom. This concludes the calibration of the cup and vane meteorological measurement systems. I invite you to read up on meteorological monitoring, and a good place to start is the EPA's QA Handbook Volume 4, Meteorological Measurements, which is on the EPA's AMTIC website. This website is listed at the bottom of your screen. The EPA has also created video calibration procedures for other wind speed and direction systems, temperature and dew point systems, and tipping bucket systems. You will find these videos on the AMTIC website. From all of us in EPA's Office of Air Quality, Planning and Standards, thank you for viewing this video.